Today, we're diving into a whole new battleground in medicine. It's a place where nanotechnology, we're talking tech thousands of times smaller than a human hair, is being used to fight one of our oldest and toughest enemies, superbugs. And no, this isn't science fiction. This is the front line in a war we really can't afford to lose. So let's get right into it.
So let me just start with a question for you. What if a tiny bacterium, one that lives in the stomachs of nearly half the people on Earth, was officially classified as a carcinogen? You know, right up there with things like asbestos and tobacco. Well, it's not a what if. For billions of people, it's a terrifying reality.
The microbe we're talking about is called Helicobacter pylori, or H. pylori for short. And for something so ridiculously small, it casts a huge shadow over global health. See, it's an absolute master of survival, thriving in the crazy acidic environment of our stomachs, and its presence is anything but harmless. You see, an H. pylori infection doesn't just cause cancer overnight. No, it's more like a slow, destructive burn that takes years. If you follow the chain of events in this diagram, you can see it. It starts with just simple inflammation, gastritis. But over time, it can progress through all these different stages of tissue damage, and eventually it can lead to full-blown gastric cancer. This step-by-step path of destruction, well, that's exactly why it's classified as a top-tier Group 1 carcinogen. So what can we possibly do about it? Well, a huge 26-year-long study gave us a really powerful answer. It found that just by getting rid of H. pylori, doctors could reduce a patient's risk of developing gastric cancer by a staggering 43%. I mean, that's not a small drop. That is definitive proof that wiping out this one little bug directly saves lives. But here's the crisis. The very weapons we've been relying on, our trusty antibiotics, are starting to fail. We're caught in this classic evolutionary arms race, and right now, the bacteria are starting to get the upper hand. And the problem is laid out right here in these graphs. I mean, each line is a different country, but they're all telling the same really alarming story. For our most important antibiotics, the trend lines for resistance are all pointing one way, up. This isn't just a fluke, it's a global crisis in the making, and it's turning a once treatable infection into a major threat. So how is it outsmarting us? Well, think of it like a supervillain who keeps figuring out the hero's every move. Our antibiotics have very specific jobs, right? Like shutting down the bacteria's internal machinery. But H. pylori has developed these incredible defenses. It can actually mutate the exact spot the antibiotic is trying to attack, which makes the drug totally useless. It can install these tiny little pumps in its cell wall to just spit the drug right back out. Or it can hide inside this slimy protective shield called a biofilm, where antibiotics can't even get to it. So with our old heroes failing, scientists needed a new one. And they found it in a pretty unlikely place: metal. This is where the whole fight pivots, from biology to physics. And it introduces this completely new antibiotic-free strategy using metal-based nanoparticles. So what exactly are these things? Honestly, the best way to think of them is as microscopic smart bombs. They're incredibly tiny particles, thousands of times thinner than one of your hairs, and they're made from metals we all know, like silver and gold. But because they're so small, their physical properties actually change, and they become these powerful weapons that can fight bacteria on a whole new level. And these nanoparticles, they're not a one-trick pony, not at all. Their real power is in a devastating multi-front attack. So let's break down the three main ways they take down H. pylori. Okay, so the first attack is just a direct physical assault. The nanoparticles act like these tiny little depots, releasing a cloud of positively charged metal ions. Now, the surface of the H. pylori bacterium happens to be negatively charged. And you know what they say about opposites attracting? Well, in this case, that attraction is absolutely fatal. The ions are pulled right to the bacteria's outer wall, and they literally punch holes in it, causing the whole cell to just fall apart. And you can see that process happening right here. The ions just swarm the bacterial cell, they latch on, and they completely disrupt its membrane. This isn't some subtle chemical trick. This is a brute force assault that the bacterium's defenses just can't handle. The second strategy is an inside job. Once they're inside the bacteria, or even from the outside, these nanoparticles can trigger the production of something called reactive oxygen species, or ROS. The best way to think about this is like creating cellular rust. These ROS molecules are super toxic and unstable, and they just create a wave of total chaos inside the bacterium, shredding its DNA and destroying its proteins from the inside out. And the evidence? I mean, it's just devastating.
Look here. On the left, you've got a healthy, intact H. pylori bacterium. On the right, after it's been exposed to nanoparticles and the ROS they create, you can see the cell membrane is ruptured, it's collapsing, it has been completely ravaged. Now, this third attack, this is maybe the most futuristic of them all. It's called phototherapy, and it basically turns these nanoparticles into tiny light-activated heaters. Certain particles, especially ones made of gold, can be engineered to absorb a very specific wavelength of light that's totally harmless to our own tissue, and instantly convert it into intense heat. This attack is all about precision. As you can see here, researchers can send these gold nanostars right to the site of the infection. Then, using a low-power laser, they basically just flip a switch. The light acts as a trigger, causing only the nanoparticles to heat up, literally cooking the bacteria to death, while leaving our healthy cells completely untouched. It's a thermal attack so fast, bacteria have no known way to defend against it. So, as incredible as all this technology sounds, you're not going to find it at your local pharmacy tomorrow. And that's because scientists still have a few pretty big hurdles to clear before this can become a standard treatment. First, there's stability. The stomach is basically an acid bath, right? The nanoparticles have to be able to survive that. Second, toxicity. We have to fine-tune them so they are absolutely lethal to bacteria, but perfectly safe for us. Third is retention. They have to stick around long enough to do their job, but not so long that they cause other problems. And finally, there's cost. Metals like gold and silver are fantastic for this, but they're also expensive. So making this scalable and affordable is a huge challenge. But here's why researchers are still so incredibly optimistic. The sheer power of this combined assault. It's not one attack, it's many, all happening at the same time. I mean, think about it. A bacteria might evolve a defense against a single chemical, sure. But how could it possibly evolve a defense against being physically torn apart, rusted from the inside, and flash heated, all at once? The answer is, it can't. This strategy creates an evolutionary dead end for the bug. And that leaves us with a final, really big thought. For the last century, we've fought bacterial infections with biology, right? We use antibiotics to mess up their life cycle. But as that strategy starts to reach its limits, this research suggests we might be standing on the edge of a brand new era, one where we stop fighting biology with biology and start fighting it with physics, using the fundamental properties of matter at the nanoscale to finally win the war on superbugs.